Hello, welcome. Today's lecture we will introduce the notion of Penrose diagram. Okay, what is a Penrose diagram? A Penrose diagram is a visualization of the global causal structure of a spherically symmetric spacetime. Well, in 4 dimensions, the metric of a spherically symmetric spacetime can be written in the following form. Okay, where here we have chosen a coordinate system adapted to the spherical symmetry. In the sense that there are constant sets are sets of transitivity of the isometry group. Which for the spherical symmetry is well known that it's isomorphic to SO3. Okay. Well, of course, here the functions a, b, and c are arbitrary but compatible with the Lorentzian signature. Okay. Well, what does this mean? Well, it means that the metric can be split in 2 parts. The first part is the so-called Lorentzian part, which is a 2-dimensional metric which has Lorentzian signature. Okay, so this is a 2 Lorentzian metric with Lorentzian signature. And here we have the spherically symmetric part. Okay, which is just the metric on on the sphere. Okay, so this is just if we take R constant, this is the metric on S on the 2-dimensional sphere. Okay, so this is the general structure of a spherically symmetric spacetime in dimension 4. So our aim is to study the global causal structure. Well, in previous lectures, well, if you listen to the lecture about the conformal compactification of Minkowski, the sitter or anti-de Sitter, we explain a procedure to study the global causal structure of those spacetimes, which amounted to constructing their conformal compactification, and from that we obtain what we call the conformal diagram. Here, of course, one could attempt the same thing, but in general, these are more complicated metrics, and that procedure would be difficult. So what we could do is just pick the Lorentzian part and carry out the conformal compactification of this part only, and that will give us the information we need about the global causal structure, because this other part doesn't have any influence on the global causal structure. Okay, let me just explain this in a bit more of detail. Okay, so, well, since the Lorentzian part is two-dimensional, then we can just find a coordinate transformation which only involves the two-dimensional part. Okay. Such that that Lorentzian part is brought into a conformally flat form. Therefore, the metric takes the following form. Now R is a function of the new coordinates, and we have the spherically symmetric part, which we didn't change. Okay, so it remains the same, right? And so the idea is just to concentrate on this part now and apply what we learned in previous lectures when we studied Minkowski, de Sitter and anti-de Sitter, to this case. Well, let me just remind it very briefly, just if you don't, for the people who don't want to list, who didn't listen to those lectures. So just take this function and define its zero set. Okay, so which is a subset of the plane R2. Then, well, if we just do a picture of the plane R2, okay, so let us just do a representation of this zero set. Okay, so just imagine that this takes this form of, okay, so this is the graph of omega tx equal to 0, and well, at those points, if we just look at the metric, at the expression of the metric, we have a singularity. Okay, so the metric is not defined at those points. Okay, but also we have an additional singularity at those points in which R, capital big R, is equal to 0. Okay, so we also have to consider points such that big R is equal to 0. Another subset of R2. Okay. Okay, which is again a singularity, and I don't want to. It's not relevant now whether these are two curvature singularities or coordinate singularities. It's just these are just regions in which the metric is not defined, and so our space-time will be defined outside those regions. In principle, we are interested in a region in which whose closure is compact. For example, in this picture, the region in which we have chosen to represent our space-time is a compact one. It's a region such that its closure is compact. Well, we could have chosen the exterior, but in the applications, we're interested in regions with compact closure. And well, we will see through explicit examples that this can be achieved. In that, well, we can choose coordinates in such a way that our space-time fits within a compact set. Okay, and well, this kind of picture which you are seeing here is what we call a Penrose diagram. Okay, and what is the interest of finding this representation of the space-time? Well, the interest is that since the metric here in this plane takes this conformally flat form, then it means that we can draw easily light rays because, well, when the metric is the two-dimensional flat one, then we know how light rays look like. Okay, they are just straight lines whose slope is 45 degrees. Okay, so if I just take I can, if I just draw I can draw a congruence of light rays in this space-time. Well, maybe I should just do it in another picture because otherwise it's going to be difficult to understand. So, for example, just take the representation of the space-time which we have, found. Which looks like this. And then draw a congruence of null rays, which we know what they look like because our metric is conformal to the flat two-dimensional one. And so here we know what light rays look like. Okay. Yes. No, I don't. Let me just take this to the other side because otherwise it's going to be okay. Okay, so the point, the relevance of knowing the generators of null rays is that we have this picture. It's easy for us to draw causal curves. Okay, so we can just draw a causal curve here because we only need to keep the tangent vector to the curve within the tangent vectors of each of the null rays, okay? So we can easily draw a causal curve, and if we have managed to fit our space-time within a compact set, then it's also easy to draw a causal inextendible curve, because a causal inextendible curve is going to be a curve whose endpoints are on the boundary of the space-time, okay? So we'll be able to visualize causal curves in this representation, and that will give us a clue. Well, that will give us important clues about the global causal structure of our space-time, okay? And since, well, of course, you may ask, well, but you are doing this in only a part of your space-time, which is the part represented by this plane. Well, that's correct, but the spherical symmetry warranties that this is enough to gain understanding about the complete space-time. Well, just notice that each point of in this diagram represents a two sphere. Okay, so if you want to imagine this representation in full, in 4 dimensions, then you need to think about each point of the diagram as a two sphere, okay? Okay, so this is the theory, the definition. Now let us just present examples of this, because just by looking at examples we will gain understanding of what is happening. Indeed, we have already studied examples in the lectures about the conformal compactification of Minkowski, de Sitter, and anti-de Sitter, but I will just review briefly the case of Minkowski, which, as I said, it was already explained, but just for the people who didn't listen to that lecture. So let us just construct the Penrose diagram of Minkowski. Okay. Well, Minkowski is a spherically symmetric solution, and we all know the form of the metric in spherical coordinates. Okay. And so, okay, so we have to take this expression and do what I said before. And well, here we can find a coordinate transformation which brings the metric in the appropriate form. So if we just perform this transformation to the metric, then what we get after some manipulations is the following. where now I am using the notation d omega q squared to represent the spherically symmetric part. Okay. So, and here, well, it turns out that this expression of the metric is of the form is of this form. Okay, so we can use the expression, this expression, to draw our Penrose diagram. Okay, so we need to find the zero set of the conformal factor. Okay, and we also need to find the zero set of this function, which corresponds to what I called before. Well, this corresponds to this function. Okay, and so the representation of these two sets will give us the Penrose diagram. Well, we already studied this in the lecture about the conformal compactification of Minkowski spacetime, but again, for those who didn't listen to the lecture, I will just very briefly review the solution. Okay. Here it's yes, this here below. Where n is an integer. Okay, right. So we can represent now this in a two-dimensional picture. Okay, we can just draw the two-dimensional plane, and well, it's easy to realize what we have. We have straight lines. Sorry, just draw the line straight. Okay, and then another line. Okay, I think I have to move this a bit. Well, okay, well, I didn't get a very nice picture, so I think it's better that I just paste in a graph which I already prepared for you, because otherwise this is not going to be very illustrative. So just give me a second. Okay, so this is better. Now this is not U, this is big R, and have to make some changes here. Okay. So okay. So this is T equal. Okay. 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 So we have these lines which which correspond to this set, and then of course we have these lines which are just vertical lines. Okay, so we have these vertical lines, and of course we have the axis itself, which corresponds to this set. Okay. Okay. So well, maybe I should just draw the vertical axis in blue, just to stress that fact. Okay. Okay. So and so now our Penrose diagram is a set which is bounded by these sets. Well, in fact, this picture gives us an infinite set of Penrose diagrams, but we only need just one. And so any of the diagrams could be, it's valid, but I'm just going to pick up, sorry, just use the black pen. So I'm just going to pick a set which is bounded by these sets. Okay, and so this set here corresponds to this representation. Okay, and gives us the Penrose diagram of Minkowski space-time. Okay, so I can just what is okay? We can just take this set and draw it separately. Okay, so I'm just going to draw. Okay. Well, this is not. Okay. So yeah, so this represents this region. Okay. This. Okay, well, and this is the Penrose diagram of Minkowski. Okay. Right. Well, we actually have already discussed this diagram when we discussed the conformal compactification of Minkowski. Well, just if you didn't listen to that lecture, just remember that this metric represents the Einstein static universe. And well, we already discussed how to get the global structure of Minkowski using this picture. Okay, well, as I explained at the beginning of this lecture, it's now easy to draw causal curves, causal inextendable curves here. And so we have a visual representation of Minkowski. Well, and just remember what I said regarding the null rays. So we should bear in mind that causal curves are curves whose tangent vector is a vector with a slope which cannot exceed 45 degrees. So that's why it's so easy to draw causal curves. And well, we see that well, this was discussed in the lecture about the conformal compactification of Minkowski, but well, we explained what this red boundary is, but well, we can just see it here if we take well, if we take now this function, okay, take this function. Well, this is now a function which is a function of r and t. Okay, well, let me just put t first and r later. Okay, so and so, well, we can compute explicitly the limit of this function when capital T and capital R approach this boundary. Okay, we can do that. Well, let me just show you the computation. Okay, because well, we know the explicit values of t, so we can just compute now the limit we can also compute the limit equals to, okay, and well, is an easy exercise. I'm just I have to connect. I need to get more. Okay, so I can just and what you have to bear in mind because we are approaching these straight lines from the interior of the triangle. So that's why I'm writing these conditions, which represent say that we are in the interior of the triangle. Okay, so if we impose those conditions on this expression, okay, then you deduce that these values. So what it means is that this red boundary corresponds to in our original Minkowski spacetime corresponds to points in which small r is infinite. So this corresponds to the infinite. So I can just write here small r equal to infinite, small r equal to infinite. Okay, and so well, if you remember, if you look at the lecture about the conformal compactification of Minkowski, then we had a special name for these points, which we call future null infinity and past null infinity. Okay, so I'm just going to write this here in round brackets. Okay, and then we also define I naught, which is the point in which space-like curves go. Okay, so because now we can also draw here space-like curves and see that this is the point which is approached by space-like curves, and we also define future time-like infinity and past time-like infinity. Well, I'm not going to say much about this because, well, this was already discussed in the lecture about Minkowski. I only want to stress here that all that information can be extracted by looking at this two-dimensional diagram. Okay, and yeah, and so we will use this information to study the global causal structure or more complex solutions of the Einstein equations. Okay, right. So, and what is going to be what is going to be our next example? Our next example is going to be the Schwarzschild solution. So we are going to see how one can use this to construct the Penrose diagram of Schwarzschild solution. Okay. Okay. Okay, well, let us start by writing down the line element of the Schwarzschild solution. These are the so-called Schwarzschild coordinates, and we see that these coordinates are already adaptive to the spherical symmetry. The only thing which we have to bear in mind is that these coordinates, as the metric is written, it represents two separate space-times. You can, well, maybe you can also speak about two separate regions, which are given by these conditions. Okay. Well, maybe to be consistent with okay, well, we can just keep this terminology. So because R equal to M is a coordinate singularity. This is very well known. So what this means for us is that we need to construct Penrose diagrams for each of these regions, okay? And what we are going to see after we construct Penrose diagrams of each of these regions is that by following some rules, which I will explain, we can match the Penrose diagrams to get a new Penrose diagram, which will be the Penrose diagram of what it's called the Kruskal extension of the Schwarzschild space-time, which is a new space-time which contains each of these regions as a subset. So in this sense, we will show how one can use Penrose diagrams to construct extensions of space-times and get a picture of the global causal structure. Okay, right. So since we have our metric in spherical coordinates, we have to apply what we have already explained. Okay, so we take the Lorentzian part of the metric and we start working with this Lorentzian part. Okay, so well, and how do we do that? Well, it's very simple. All we need to do is a coordinate transformation. Okay. Maybe I should, okay. By doing this coordinate transformation, we get explicitly conformally flat metric, but the point is that well, it's not difficult to realize after, well, one has to find one has to integrate, has to find the explicit relation between big R and small r. Okay, so this is just an integral. Okay, well, you can just check that the result of this integral is given by this expression. Okay, and well, the thing is that, well, by looking at this expression, we realize that big R varies within an infinite range. Okay, so what this means is that even though we have a conformally flat expression for our metric, we won't be able to get a compact representation of our space-time, as we explained before. So we need to do a further coordinate transformation here to get the compact representation. Well, and the coordinate transformation which we need is is similar to the case of Minkowski, which we just explained, and well, this is transformation appears quite frequently when discussing Penrose diagrams. So just going to write the transformation once again. So we are using variables names which are different to the Minkowski case. Okay. And so after doing this transformation, we get well, I think I can just write the result here. We get the following representation for the Lorentzian part of the metric. Okay. That's the conformal factor, and then the metric, which now it's conformally flat. And well, as we already know from Minkowski, and I will remind in a minute, now coordinates vary within a, this new coordinates capital T and U vary within a compact set. Okay. Well, just have to mention that now small r has to be regarded as a function of the new coordinates. Okay, so this arc which you see here is indeed a function of T and U. And how one gets this function? Well, this function is obtained by inverting this relation and replacing. Well, it's just that. Well, it's obtained by inverting this relation and replacing big R with this expression. Right? Okay. Right. Before, yeah, okay. So let me just mention that why this, or well, remind why this vary within a compact set, because, well, we have to now study the zero set of the conformal factor. Well, indeed, what we need to just to follow the notation which set at the beginning of the lecture. Here, the conformal factor is just the inverse of this expression. So I have to write this divided by this. Okay. Right. Well, and also notice that since we are assuming that r, small r, is different from 2m, then this denominator is always different from 0 for each of the regions we have to study. So we need to concentrate on the zeros of this factor, and well, this is exactly the same as for the same factor as the one which we had in Minkowski. So I only need to go back to the study which we did for Minkowski, and well, I have to redraw this diagram, but adapted to our situation. So that's what I'm going to do next. I'm just going to draw the picture. Well, actually, what I'll do is just paste in the picture, and well, this is just well, these lines represent the zero set of the numerator. It's exactly the same as in Minkowski. Okay. Right. Okay, so that's the situation, and so we need to identify which region in this picture will correspond to our Penrose diagram. But since we are dealing with two different regions, as I explained at the beginning, then we have to do that for each of the separate regions. We have to separate both cases, and that will give us two or maybe more independent Penrose diagrams. So let us start by assuming that the small r is greater than 2m, okay, which is the so-called exterior region. You will see why. Okay, then okay, what happens in this case? Well, to find out what happens, well, we need to look at this expression. Well, let me just take this expression, okay. And paste the expression here. Sorry, but before we well, there's something which I forgot to mention, and it's just that we need to well, okay, I can do it. I can mention that later. Okay, so let's concentrate let's discuss this case. So take this relation, okay, right. And so, well, we only need to know qualitative behavior of this function, okay? And so, to find out this behavior, it's enough to draw a graphical representation of this function, okay? So I'm just going to so this is small r, this is big R. Well, you see that r equal to m. We have divergence, right? So graph will look something like this, okay? Right. And well, for the moment, since we are dealing with the case r bigger than 2m, we only need to care about one side of the graph, right? Okay. So yeah, this is one thing, and now we need to find out which regions of our space-time, of our original space-time, these lines correspond to, okay? And how do we do that? Well, we do that in a similar fashion as we did with Minkowski. Is just by computing the following limits. We study the value of big R when it approaches each of the lines. Okay, that's what we are doing by computing these limits. Okay. this computation is recurrent in the study of Penrose diagrams. Okay, so this is the result. Well, this is an exercise of analysis. Okay. Indeed, this is independent on the region which we are working. So I can just draw in the diagram the result. So this is equal infinite. This is r equal infinite. This is r equal minus infinite. I have to just minus infinite. This is r minus infinite, small r. Okay. Okay. So yeah. So as I say, this result, which I have just written, has nothing to do with us being in the exterior region, because we obtain it by just computing this limit. Okay. So and just remind that we are approaching from the inside, and the reason why we are approaching from the inside is because we have picked this central square as the region which will represent our space-time. Well, I didn't mention this, but well, okay, as before, we could have picked any of the because, well, this is an infinite set. Okay, it's the same as Minkowski, and we could have picked any of these squares as a representation of our space-time. Just remember that we need to pick a set which is bounded by the conformal factor, by the zero set of the conformal factor, and so we just picked this one. And so since we picked this central square, we need to compute the limit coming from inside. And this is what this is what has been done here. Okay, so okay, so once we have been done this, we just go for the study of this particular case. And so we need, in this particular case, we need to check which values of small r the values here of big R correspond to. And how are we going to do that? Well, it's very simple. We only need to look at this graph, and well, since small r is greater than 2m, we only need to take into consideration this line here. So I'm just going to delete for the moment the other part. And so by looking at this, we see that when big R goes to infinite, small r goes to infinite, and when big R goes to minus infinite, small r goes to 2m. So in this particular case, and only in this particular case, I can just take the graph here, okay, paste in the graph here, and then replace these values by the values of small r. Okay, so this is small r infinite. This is, I have to replace small r infinite, and here small r is equal to 2m, and small r is equal to 2m. Okay. Right. And yeah, another important issue which we have to take into consideration is the time orientation, because yeah, okay, so we have this picture. Well, here, as I said, the square is represent our space-time, but we need to check which what is the time orientation and how do we do that. Well, we just look again at the expression we got for the Lorentzian part and just check the sign of the conformal factor. Since we have that small r is greater than 2m, it means that in the exterior region the conformal factor is positive. Okay, don't have to put this here. Okay, this has nothing to do with this. Okay, and so since the conformal factor is positive, then we just have to check that the expression of the metric and realize that big T represents time. So it means that here time direction goes along big T, along the T axis. So I can just draw an arrow here to represent that we have the time orientation going along the big T axis. And also, well, remember that also I said that in addition to the zero set of the conformal factor, which we have been considering, we need to consider the zero set of this function. Okay, because, well, just remember the explanation at the beginning of the lecture. But here in this case, well, since by assumption big R, small r is greater than 2m, it means that when we rewrite small r in terms of the new coordinates, we will never get a value of big T and u such that small r is 0. So it means that in this case, this function du is indeed different from 0. Okay, so we don't need to worry about the zero set of this function because it doesn't exist. So we conclude that the Penrose diagram for in the case in which small r is greater than 2m is represented by this square with this time orientation. Okay. Okay. Well, this is very very simple. Okay. So we have already obtained a Penrose diagram, right? Okay. And what about the case in which small r is less than 2m? Well, remember that small r equal to 0 is a curvature singularity, so we don't need to. So okay, we have this relation, and yeah, so in this case, well, what we have to do now is to, well, this picture doesn't is independent on the case which we are studying, so we still have to work with this picture. But now I have to take this graph and add the remaining part of the other part of the curve which I deleted before. Okay, and well, I can now I can delete this part because we're assuming that small r is less than 2m. Okay, this is 2m, right? And so what we have to do now is we need to check how these values of big R relate to the values of small r. But again, that's simple because we only need to look at this graph and see what happens. And we see that if r goes to plus infinite, then what happens here is that this curve intersects the vertical axis here at a certain point. I should have drawn this axis larger, so I should have a larger axis, and so we have an intersection of this curve at a certain point, which we can compute from here. So it's just set small r equal to 0, and we get that r naught is just this value. Okay, right. So it means that when the value big R going to infinite doesn't exist, because big R never gets to infinite when small r is positive, and so we need to check the value small big R going to minus infinite, which corresponds to, well, just by looking at the graph, it corresponds to r equal to 2n. Okay, yes, write this properly. This is 2n, right? Okay, so let us just take take this picture. With the value of r naught included, and let us just bring it here, right? Okay, so we said that r equal to minus infinite corresponds to small r equal to m. Small r equal to m, and then this value is never attained, and now we have to study the zero set of the function RTU, which is the composition of R with big R TU. Okay, and well, again, we have to look at the graph of we have to look at this graph. Let me just take this graph with me. Okay. Just put it the graph in here, right? Okay, so we have the graph, and so yeah, if small r is equal to 0, then we see that big R is equal to r naught. So we conclude that this condition is equivalent to the condition RTU equal to r naught, where r naught is this constant value. Okay, and since we have the explicit expression of big R, so we only have to study the well, just remember, let me just put this a bit further up. because otherwise it's going to be complicated. So since we have the expression of big R is here, okay, so we just need to study the the graph of this function, okay. Okay, so that's what we need to do. And yeah, well, there are different ways of doing this. We can take a computer program which draws graphs or whatever, but the solution is just that this graph it's represented by this curve, okay. So you can just draw the graph. This is just r equal to 0, right? So it means that since this is r equal to 2m and this is r equal to small r equal to 0, then it means that our space-time is now represented by this compact region, okay. So this compact region is the Penrose diagram in the case in which we are in which this condition is satisfied, and well, this defines the so-called interior region. You will see why next, but okay, right. So and then, well, we need to also take into account the sign of the conformal factor. And now, well, if we just look at the conformal factor, well, numerator always positive, but now denominator, if small r is less than 2m, denominator is negative. So it means that the conformal factor in this case is negative. And so by looking at the expression of the metric, we deduce that now small u will represent time. So to summarize here, what we have is that this is not, it's just this one. So we have that conformal factor is negative now, and so it means that the time orientation goes along u. So now we have that. I'm just going to. This represents the time. Okay. So this is now the time orientation, right? Okay. So we have now the complete Penrose diagram of this case. And now, well, okay. So let us just summarize and draw the Penrose diagrams of both regions, the exterior region and the interior region. I'm just going to paste in the Penrose diagrams which we obtained. Okay, so this is. I think this is one of the Penrose diagrams. I think we can the Penrose diagram of the exterior region, and just remember. Well, okay. I think I have just deleted the axis, but I still need the axis for something. So, well, I think I'm just going to take this away and paste again the diagram. Okay, so this is the Penrose diagram of the exterior region, and then the Penrose diagram of the interior region. Okay, and well, we need to remember the time orientations. Time orientation in the exterior case goes along t. So I'm just put this blue arrow to indicate the time orientation, and here time orientation goes along u. Well, just to remember, goes along u. Okay, so I just have to draw this blue arrow to indicate the time orientation, right? So we have to these two diagrams, and now, well, we need to take into account that if we do the following transformation here in this diagram, then if you look at the expression of the metric, the metric doesn't change, but here the diagram does change. We get another diagram in which is the reflection with respect to the vertical axis. Okay, so I just have to perhaps move this here just a little bit and take this diagram, paste it in. Okay, well, and then, well, have to have to move the labels to do the reflection. Okay, okay, and time orientation doesn't change. So okay, so this is just after doing this transformation. And in this other diagram, well, if we do the same transformation, then, well, again we have a reflection with respect to this axis. So what we get is let me just move this. Here, okay, so in this case I have to do this. Yeah. Now time orientation does change, and I have to redraw the r equals 0 set. Okay, so this is r equal to 0, and this is well, now time orientation goes in the opposite direction after doing the reflection. Okay, so this is what we get after doing this same transformation, right? So I get this. Okay. Okay, so in the end we have ended up with not 2 but 4 independent diagrams. Okay. Okay, now the point is that we are actually able to join the diagrams in a bigger diagrams according to the following rules. The diagrams have to be matched according the diagrams have to be joined through matching sides. We can only join through regions with the same labels, and also we need to keep the time orientation when we join the diagrams. Okay, so well, let us do that, and so you will see how this works. Okay, and you don't need this. Well, also, since well, okay, you don't need this. For example, let us just take this diagram. Okay, so let's just put the diagram here. Okay, we no longer need the axis, so I can now delete the axis. Okay, so let me just type orientation in the center, and well, can just complete this line, right? Okay, so well, we need to attach to this diagram or more diagrams. As I said, we need to do it through matching sites. For example, I can take this diagram here. Okay, let me just take this diagram and let us see how can we match these two diagrams. Well, we can do certainly do that, but because there are matching sites, but as time orientations are not matching because the arrows point along different directions. So what it means is that we have to rotate this diagram to have matching time orientations. Okay, so well, let us do that. So I have to delete here some stuff here. Okay, we no longer need this, so I have to just put this here, okay. And now, well, you just remember, so this is the blue line which corresponds to r equals 0. This is the time orientation, right? So and well, we don't need this because this is a region outside of our space-time. Okay, so we can just take this and match through this side. Okay, so you see that we are matching through r small r equal to 2m, and time orientations are kept. Okay, so by doing this we have obtained a bigger space-time now. Okay, and well, this is actually the Penrose diagram of a bigger space-time, which is a union of regions represented in our original metric. But well, if you look at this picture, you see that there are still more possibilities because, well, of course, we cannot match through. Well, okay, I said that we should match along sites with the same labels, but of course, these labels should represent a specific hypersurface. This is r equal to infinite, which doesn't represent a hypersurface, and here this is r equal to 0, which corresponds to a curvature singularity. So we are not allowed to match through these sites. We can only match through small r equal to 2m, and so that's what we have to do. Okay, for example, take this diagram here, and okay, so we have this diagram, and here we notice that we do have matching sites, and we have a matching time orientation, so we can join. Well, let me just delete what we no longer need. Okay, so it's no longer needed. It's no longer needed. No longer needed. Okay, so yeah, we take this and match through this side. Okay, and yeah, and so we get a Penrose diagram of a yet bigger space-time. And here, well, we see that we still have some room for further matching here. Okay, so let us go up and see what else is left. And so we take this diagram here. Well, we realize that it's still possible to match, but well, to keep time orientation. Well, okay, but it's not. We need to. We need to rotate this diagram. Okay. So let me just. How can I do this? Okay, I think that. Okay, just. Okay, sometimes things are a bit complicated, but I hope that you understand. Okay, so this is r equal to infinite, and then this was r equal to m. So we need to rotate to match this to match through r equal to 2m. So that's what I'm going to do now. Rotate. But we no longer need this, so I just delete this. So delete this, and okay, so well, okay, just like to do this with the thin pen. Okay, this is equals 0. This is no longer needed, right? And now, well, if we rotate, time orientations goes this way. But well, I must say that time orientation, well, since this is a time orientable space-time, I'm talking about this space-time now, we can change, we can choose another time orientation, because I mean, as it stands now, this time orientation is not compatible with the time orientations of the other regions, but I can just pick another time orientation here. So I can just reverse the arrow and make it point into this direction, okay? And so after changing time orientation here, is now possible, we can now match. Well, not match, but I have to get closer, okay? So now we can match the diagram, okay? And so we get this diagram, and if you look at this diagram, well, now time orientations are consistent in all the regions, and well, it's not possible to add further diagrams here, because as I said before, we cannot match through r equals 0 or r equals infinite, okay? So we have obtained a diagram which cannot be extended anymore, okay? Okay, and well, what is the meaning of this diagram? Okay, well, this diagram is the Penrose diagram of the Kruskal extension. Okay. Well, right. Kruskal extension is the so-called maximal extension of Schwarzschild, and well, it was obtained explicitly by Kruskal by doing coordinate transformation, by constructing explicit coordinates which cover a space-time which represents this complete region. Okay, and we have accomplished that extension, but without doing any coordinate, without constructing any coordinate representation. We have just achieved that by joining Penrose diagrams, and this is one of the applications of Penrose diagrams. Penrose diagrams allow us to build extensions of space-times without doing any coordinate transform, without constructing any coordinate system. We started from the Schwarzschild metric, which was only valid for two regions, which we call the interior region and the exterior region, and by constructing the Penrose diagrams of each of those regions, we have constructed constructed a Penrose diagram of a bigger space-time, which represents the Kruskal extension. So Penrose diagrams are useful to construct extensions. Okay. Okay, and the extensions are constructed by joining Penrose diagrams according to the rules I said. We have to match through regions with the same labels and regions which represent hypersurfaces on our space-time, and we have to keep time orientations. And well, if some time orientation don't match, we take advantage of the fact that we are dealing with a time orientable space-time, and just change the time orientation, pick another time orientation. But in the end, we need a consistent time orientation, okay? Which is well, just put it in blue, because the extended space-time is time orientable. Okay, but leaving aside that, what can we learn from the global causal structure of the Kruskal extension once we have its Penrose diagram? Well, we have well, a lot of information, in fact. Well, the first point is that we have two asymptotically flat regions, okay? Because what do I mean by that? Well, if you just look at this set, or you look at this set, you see that these two sets, well, the Penrose diagrams of these parts look pretty much the same as the Penrose diagrams of Schwarzschild space-time, sorry, of Minkowski space-time. So when that happens, we suspect that we have an asymptotically flat region. Okay, this is not a formal proof, but the diagram allows us to say that we have asymptotically flat regions, okay? So, well, let me just label, well, I'm going just to delete the arrows, which gives us the time orientation, because we don't need them anymore. And so we only need to know that okay, this is not needed anymore because we have already labels here. Okay. Okay, this is not needed anymore, and so we're just going to give a name to the regions, which we call asymptotically flat. And well, if you remember our analysis, these regions correspond to what I called before exterior region. Okay. So yeah, exterior of what? well, exterior of an interior, which is going to be a black hole. And why do I say that this is a black hole? Well, because, well, we just take advantage of a Penrose diagram, which and allows us to draw causal curves very easily, because we just have to remember the prescription of the slope of the curve. So, for example, if we have an observer coming from far away, well, this observer can approach the boundary of region 1, and he can enter in this other region, and once he enters in these regions, there's no way for him to come back to region 1 or approach region 2, because if he tries to approach region 2, he would have to follow a space-like path, which is not possible for an observer. So he will end up in r equals 0, which is a singularity. And the same happens for any observer which starts in region 2. So the bottom line is that an observer which leaves either region 1 or 2 and enters these other regions, which we will call region 3 and region 4, okay, then he can no longer return to region 1 or 2, okay. And so, well, this corresponds to the definition of a black hole. A black hole is a set in which once you enter, you cannot get out. And you cannot get out because to get out, you would have to speed up to a speed which is higher than the speed of light. So it's, well, we can see very easily in this diagram that if you enter in region 3 and 4, you cannot return to the asymptotically flat regions. So that's what we were calling region 3 and, well, region 3 and 4 correspond to what we call interior region, and it's an interior of a black hole. That's why we're using the name interior, okay. Okay, so yeah, so the diagram shows us very clearly the black hole nature of the Schwarzschild space-time. Well, also we can read off the topology of this space-time. Well, just remember that in a Penrose diagram, each point of the diagram represents a sphere, okay. So, since each point represents a sphere and the topology of this two-dimensional region is R2, then we deduce that the topology is just S2 R times R, okay. Well, more features. Well, for example, well, we can just see the causal character of the singularity, because if we just look at this picture, this is a space-like set, okay. So, well, just well, this is just one of the advantages of using a conformal representation, and is that we can just speak about the causal character of something which we couldn't speak of if we were inside the space-time. Well, just remember that we are looking at the Kruskal space-time from the outside, and that enables us to see or define things as the shape of the space-time. And so, in particular, we have the shape of the singularity. So, and the fact that this singularity is space-like implies that once an observer enters any of the black hole regions, in this time orientation, region 4 is in the future, is the future black hole region, and region 3 is the past black hole region. Then once an observer enters region 4, then he cannot leave region 4, and in fact he will hit the singularity no matter what he does. So this singularity cannot be avoided, and the observer will get destroyed by the singularity. Okay. We are just this is just only by looking at the Penrose diagram. Okay. Okay. Well, in fact, in the asymptotically flat part, we can use the terminology which we use when we studied the conformal compactification of Minkowski. You just look at the lecture about Minkowski. We introduced a number of ideal regions and points, which I am just putting here. Okay. Okay. And so, well, I'm just using the same points because these correspond to an asymptotically flat region. Okay. Also, well, these hypersurfaces are special in the sense that, they serve as the boundary between the exterior region and the exterior regions and the black hole regions, and so it's just the now return point, because once you drive past this hypersurface, you are in region 4 and you cannot get back. So this is what is called an event horizon. Okay. Well. Okay, so and another thing which can be guessed from the diagram is that this is a globally hyperbolic space-time. Well, just remember from the Minkowski for the conformal compactification of Minkowski, the definition of global hyperbolicity, well, it's just that there is a Cauchy hypersurface. I'm just going to draw a Cauchy hypersurface here. Okay. So doesn't fit. Okay, and again, this is very easily seen in the diagram because, well, just taking advantage of our ability to draw causal curves, we can just see that any causal curve, any inextensible causal curve, it means a curve which has a endpoint on the boundary, conformal boundary, will have to cross this hypersurface sigma. Okay, so if you draw any inextendable causal curve. In this picture, you will see that it would always cross the Cauchy hypersurface. So this is globally a hyperbolic space-time. Well, as I'm always, this is not a proof, but just the diagram enables us to guess that this is so. Okay. Well, and also, well, I would like to comment on a special point, which is this central point, which is the point in which the hypersurfaces representing the event horizon intersect. Okay, well, since this is a point of the diagram, it's a point which has topology of S2 of the sphere. Okay, this point is called the bifurcation sphere. Well, we are paying attention to this point. Well, because this point appears in general black holes. Well, it can be seen as the, well, just by looking at the diagram, we see that it's the point which connects the two asymptotically flat regions, 1 and 2, and well, it can in a general black hole, in which it can be defined as the intersection of the future event horizon and the past event horizon. Okay, well, we see that there are a number of event horizons here, and they intersect at this point. So in a generic black hole, we are supposed to have well, actually, well, maybe it's better that, well, just by looking at this diagram, we can just draw a diagram of what we may of what a generic black hole might be. So we will have a asymptotically flat region. Okay, so this is going to be something like okay, and then we will have a future event horizon and past event horizon. Okay, okay, and then inside here, well, something which we don't know about. Okay, well, maybe singularities. Well, in our case, we have singularities, but well, it doesn't have to be the case. It could be something else. But the point of generic definition of a black hole is a symptotically flat region plus future event horizon and plus event horizon. Okay, and so the set in which the future event horizon and the past event horizon intersect is what is called the bifurcation sphere. So this is supposed to exist in a generic black hole. Okay. Okay, so we see that just by looking at this diagram, we can learn about a great deal about the global structure of a black hole. Okay. Okay. So, well, and just coming back to Schwarzschild, in this case, well, if you just look at the structure of Schwarzschild, this corresponds to the so-called Rosen throat, also called Einstein-Rosen bridge. Okay. Okay, so as I was saying, we have learned a great deal about the Kruskal extension of Schwarzschild spacetime without actually doing the extension, just by putting together some Penrose diagrams. So in coming lectures, we will study diagrams of other solutions of the Einstein equations, which also represent black holes or cosmological models. Okay. Okay. Thank you for your attention, and see you in the next lecture. Bye bye.